This is section 3.8, Invariant Distributions 2. It's a continuation of the last section where we mainly dealt with invariant measures. So we are going to deal with invariant distributions here mainly. Let me quickly summarize what we saw in the last section. First of all, we saw an existence theorem that said that on a communicating class that is recurrent, there is always an invariant measure. Yeah, these were the pi bar that we defined there. They are invariant measures and they are positive and finite. Then we saw a uniqueness theorem that says that on a recurrent communicating class, all the invariant measures are essentially the same. They are the same up to constants, up to constant multiples. This section, as I said, deals mainly with invariant distributions. And the first theorem we are going to show is that if there is an invariant distribution, then those I with pi I positive, so where the invariant distribution has mass, are recurrent. So that's in a sense a partial converse of the existence theorem that you saw. Recurrence implies existence of an invariant measure. Existence of an invariant distribution implies recurrence. In particular, we're going to deduce that on transient classes, there are no invariant distributions. However, there are invariant measures typically on transient classes, and they are usually distinct in the sense that they are not only constant multiples of one another. So the uniqueness theorem that you saw on recurrent classes does not hold on transient classes. And finally, we're going to see a relation of the invariant distribution, if it exists, to expected return times. This is the program for this section. Let me start this section by repeating part of the results from the last section again. So we saw in the last section that on a recurrent class, so let me underline this, on a recurrent class there is always an invariant measure, and invariant measures, or different invariant measures, differ only by constant multiples. In particular, there is at most one invariant distribution on a recurrent class. Why is this? Well, assume you have two distributions, two invariant distributions on the recurrent class. Then these two invariant distributions are also invariant measures, and by the first sentence there's a constant such that pi tilde is constant times pi. But this constant has to be 1 because, the sum of the pi I tilde is 1 and the sum of the pi I is also 1. So, C has to be 1. And pi has to be equal to pi tilde. The next theorem is some sort of converse. It says the following. If there is an invariant distribution, and I'm stressing that we have to assume distribution here, on E, then all j with pi j positive are recurrent. In what sense is this a converse? Well, the previous results from section 3.7 said if we are working on a recurrent communicating class, let's say the whole Markov chain is recurrent, then there is an invariant measure and it's unique up to constant multiples. And we have this additional thing that there can be at most one invariant distribution. And in a sense, the converse is if there is an invariant distribution, notice that you have to assume distribution, not measure, so this is not exactly the converse. If there is an invariant distribution, then all j such that pi j is positive are recurrent. In particular, if the whole Markov chain is one communicating class, then the Markov chain or the whole set E is again recurrent. Let's take a look at the proof of this theorem. Of course, what we want is to use the recurrence transience criterion. So what we show is that Pjjn sum in n is plus infinity. And this implies that state j is recurrent. However, we first look at a similar sum for k not equal to j. So pkj to the n, k not equal to j. First of all, we rewrite this quantity here by its definition. So pkj to the n is nothing else but the probability of starting at state k. We are at j at time n. in the next step, I'm going to split this event, and I'm going to ask, when did I reach j for the first time? And in the event that I added here, this says that I reached j for the first time at time L. So xl is j, but xl minus 1 and so on up to x1 did not see j. Okay, so I'm going to call this piece here not before. So basically I reach j for the first time at time L. And of course these events are disjoint because I cannot reach j for the first time at 5 and then again for the first time at 7. So these are disjoint, and the union of these events is this event. So this step here is just the sigma additivity of the probability measure. The next step is sort of a usual argument that you've seen quite a few times. So instead of putting an and here, I'm going to condition on what is behind. And then of course I have to multiply with the probability that xl equals j and not before. And then I use the fact that for computing the probability that xn equals j, it's not relevant what x did before time L. Yeah, if I know that at time L the Markov chain is at j, I do not care how it arrived there. So I can erase these conditions. So that's an argument with exercise 313 that we've seen before. And then I'm going to finish my operation here by rewriting this piece here as the probability of starting in j and then being back at j at time n minus l. Yeah, so I'm moving things back to 0 because I know that I'm starting at j and I want to be back at j after n minus l steps. So this is summarized in this line here. So I splitted this sum here, and I want to start from k, then I want to be at j at time L, yeah, L from 1 to n, but not before, and then I start at j, and in the remaining n minus l steps, I want to be back to j. And this thing here is nothing else but p jj n minus l, yeah, start in j, want to be back at j after n minus l steps. The next observation is that this quantity here now doesn't depend on n anymore, so I can move it in front of this sum here. Yeah, this is the next step, and nothing else changed. Then this quantity here can be made independent of L, because this is the same as the sum n from 0 to infinity p jj n, yeah, by just an index shift. So this means we can just look at this term separately. And what does this term stand for? Well, I start at k, and then I visit j at L for the first time, and I take the sum in L. So at some point I visit j, yeah, for the first time. So I do visit j. So this is nothing else but the probability of starting in k of ever visiting j. Okay. So I've written this a little bit more neatly here. Probability starting in k that there is an L such that xl equals j, yeah, of ever visiting j. And here I copied things from above after this index shift. The next step is relatively easy, so I'm just estimating this probability here by 1. Okay, and I'm copying the second sum here over to the next step. Okay, so this is the end of the first computation. There will be a second computation on the next page which uses this. And of course we want to show that this sum here is plus infinity, and we're going to see some estimates on the next page which involve this sum, and we can replace it then by this sum at an appropriate time. So let's take a look at the second computation. We start with the assumption that pi j is positive, and we want to show that, that j is recurrent. The first step of this computation is quite weird. So if you have this positive number pi j, and you sum it up in n, so not in j, but in n, then of course summing up a positive number constant number is not a good idea. You will get plus infinity, but that's just what we want to have. The next step uses the invariance property of pi. So pi j is the same as the sum k and e, pi k p k j. Yeah, this is the invariance property. And then we know that we can do this an iterated number of times. So I'm going to write p to the n here, yeah, which is using this property n times. If you want shorthand notation, then the invariance property says that pi is equal to pi times p, and what we are using here is pi is equal to pi times p to the n. In the next step, we're going to split this sum. So we're going to split the sum in one part, k and e, k not equal to j, yeah, and then pi k p k j to the n, plus, of course, the one term that we left out here, which is pi j times p j j to the n. And of course, there's this n sum here in front, and I'm going to pull this past this sum here, which I can do by Fubini because everything is non-negative. So the n sum is applied first here, and of course also here. So that's what you see here. Ignore the coloring at the moment. So this is the sum without the j. This is the j term, and I've moved the n sums here and here. The next step uses the computation from the last page. There we saw that this blue sum here is upper bounded by the sum when you replace the k by the j. Yeah, this is exactly what we saw on the last page. And then there's another little modification. I replaced this 1 here by a 0 just to make it look very similar to the first sum. And of course, this is also an upper estimate. Now, this sum and this sum are the same, so I can factor it out. So this becomes this sum here. And what I'm left with is the sum in k for k not equal to j and the remaining term here, which of course now is the total sum of the pi k, k and e, and this is 1 because the pi is a distribution. So here we use that pi is a distribution. And now we compare the left-hand side with the right-hand side, and we see that this sum here has to be greater or equal plus infinity, which means it is equal to plus infinity. And this is what we wanted to show, because if this sum here is plus infinity, then j has to be recurrent by the recurrence transience criterion. And this finishes the proof of the theorem. There's one remark that I want to make here, which is not very important, but still we might want to use this. So this is the formula that we proved on the last page. So remember that we started with this thing here, and then we computed it, and we saw that it equals the probability of, well, when we start in k to ever reach j, yeah, times this quantity here. Yeah, and we used this, and then we estimated this by 1, and this is what we used here in this inequality. Yeah, without the inequality, I would like to note down this just for future reference, yeah, that I don't have to cite into a proof, but rather citing this remark. Here's a corollary for transient states. So it says the following: on a transient class, there's no invariant distribution. Yeah, even though we've worked with recurrent states and shown sort of equivalence of recurrence and existence of invariant measure or invariant distribution in one way or the other, we can use this to say something about transient classes. As an exercise, I would like to ask you to prove this corollary. So please stop the video and think of the explanation for this corollary. Here comes my solution. So assume that pi I in S is an invariant distribution on the class S. Then, since this is a distribution, there has to be an I in S with pi I positive. Yeah, if all the pi I are 0, then the sum of the pi I is 0, and it's not a distribution. And then by the last theorem, so by theorem 351, I0 must be a recurrent state. So I0 is recurrent. And since I0 is from S and S is a communicating class, the whole communicating class S must be recurrent. It cannot be transient. So that's what I wrote here. And this finishes the proof. So the last corollary says that on transient classes there is no invariant distribution. Of course, there may be invariant measures on transient classes. These invariant measures then necessarily have infinite total mass, because if they had finite total mass, then we could renormalize them to get an invariant distribution. And an important thing is also that the invariant measures on a transient class can be quite different, so they are not necessarily constant multiples of each other. Okay, and that's what we're going to see in the next example. And these examples are wrapped up as the following exercise. So consider the asymmetric simple random walk on Z, which means that going to the right has probability theta, going to the left has probability 1 minus theta. And your task is to show that the following quantities are invariant measures. So first of all, pi I is given by theta dividing 1 minus theta to the I. This is one choice. And the other one is pi tilde, which is the constant one measure. And you should show that these two choices are indeed invariant measures. After you've shown that, let's sit back a little and see what this means. And for this, consider two choices. First of all, if theta equals 1/2, then you see that theta equals 1 minus theta. So pi is also constant 1. So actually both invariant measures coincide. And this is in accordance with the uniqueness theorem for invariant measures on recurrent classes. Because theta equal 1/2 corresponds to the recurrent case. So in this case, all the invariant measures are the same up to constant multiples, of course. Contrary to this, in the case that theta is not equal to 1/2, which is the transient case, there the pi and pi tilde are really distinct invariant measures. They are not constant multiples of each other. And this is exactly the goal of this exercise, to understand this. So now please stop the video and show that these two choices are invariant measures indeed. Here is my solution. So before we start computing things for the pi I or the pi I tilde, let's repeat what are the transition probabilities. So we have that pi I plus 1 means going to the right is theta, pi I minus 1, which means going to the left, is 1 minus theta, and all the other transition probabilities from I are 0. So now let's show that pi I is an invariant measure. What I have to show is that the sum in k in Z, in this case, pi k times p ki, that this is equal to pi I. This is the invariance property of pi I. What is this sum? Well, the sum only consists of two terms because the p ki are mostly 0 except for two places, namely the place when k is equal to I minus 1, then we have pi minus 1I, and the place where k is I plus 1, so this is pi I plus 1, I plus 1I. And I can now insert the definition of pi I or I minus 1, so this is theta dividing 1 minus theta to the I minus 1. Then I have a pi minus 1 to I, so I'm going to the right. Going to the right means I have to multiply here with theta. And then here pi I plus 1 is theta dividing 1 minus theta to the I plus 1. And pi plus 1 I means I'm going from I to the left, which has probability 1 minus theta. Let's massage this term a little. So I'm going to factor out theta dividing 1 minus theta to the I. And in the first term, of course, I can factor out this theta to the I because it's here. I took a little bit too much here at the bottom because this is only 1 minus theta to the I minus 1. So I have to multiply by 1 minus theta here, yeah, in order to compensate for this. And here I could factor out the theta dividing 1 minus theta to the I. There is a theta left, which I have to write here. And then there's a 1 minus theta at the bottom, which cancels with this 1 minus theta. Okay, and that's the equality here. And you can see that 1 minus theta plus theta is 1, and theta dividing 1 minus theta to the I is pi I. So this is pi I. And we are finished with the proof of showing that this thing here is an invariant measure, because we've seen that, well, the sum of the pi k, p, ki is equal to pi I, which is the invariance property of pi I. Let's look at the second task. So we were supposed to show that pi tilde is also an invariant measure. So if I plug in here pi tilde instead of pi, then of course this step here remains the same. So this is pi tilde I minus 1, and here it's pi tilde I plus 1. And the definition of the pi tilde, of course, is different. So instead of writing this expression here, I have to write a 1 here. So 1 times theta. And here also pi tilde I plus 1 is also 1. So this is 1 times 1 minus theta. And then you see that this is theta plus 1 minus theta, which gives us 1. And 1 is exactly pi tilde I. And we've also seen that this thing here is also an invariant measure. And this is the end of the exercise. We now come to the very last part of this section, which is a relation between invariant distributions and expected return times. This is the following theorem. Assume pi is an invariant distribution on the then necessarily recurrent communicating class. Yeah, recall that on transient classes there's no invariant distribution. The assertion is that then you can compute, well, compute not necessarily explicitly, but you can see that pi I, so the invariant distribution at state I, is given by 1 over the expected first return time to I. So you start at I and you ask, when is the first time that I return to I? Yeah, this is t1I. As already mentioned, this will not help us to compute the pi I. Yeah, computing the pi I is best done with the help of the invariance property of the pi I. But this theorem can help us to get a relation between the positivity of the pi I and the question, when are these quantities here, these expected return times, less than infinity? I hope that this relation makes it clear why we called a state I positive recurrent if the expected return time is finite. Yeah, so expected return time to I is finite. This is the notion of positive recurrence of the state I, and this is due to the positivity of the corresponding weight of the invariant distribution. Yeah, otherwise it would have made more sense to call this finitely recurrent or something. Yeah, because the expected return time is finite or so. Let's take a look at the proof of theorem 355. The first observation is that pi, the invariant distribution, is also an invariant measure, and since we are working on a recurrent class, the invariant measures are all constant multiples of each other. So the invariant distribution pi is a constant multiple of the invariant measure pi bar that we defined before the existence theorem. So I've put the reference here for these pi bar, but you certainly remember them. We used them not only in the existence theorem, which was 346, but also after that. And we saw that in remark 349 that there was a very special prefactor here, namely the pi I. Yeah? Pi I is the constant multiple that turns this invariant measure into, well, this invariant measure, which is our invariant distribution here. Now let's look at the following computation. We're going to sum up the pi bar in K, and first of all we're going to use the definition of the pi bar. So this here is exactly pi bar Ki. So this was the expectation starting in I and then counting how often you visit k before you reach I. I wrote this in text this time, but it actually means I do not visit I before time n. Yeah? And each time I visit k, I count a 1 until I visit I, and then I don't count any ones anymore. The next step is to shuffle the sums. So I can exchange here the sums and expectation as I wish, because what I'm summing up is non-negative. The next step says the following. So for fixed k, I'm counting here, do I visit k at time n or not? Yeah. Accordingly, I write a 1 here or a 0. Now I'm summing up over all k and s. So I basically count a 1 here as soon as I have xn in s. Yeah, and that's the same as writing the indicator that xn is in s. And then of course I have to add the extra condition here. Now comes the following observation. Note that I start in I is in s, and well, then necessarily xn is also in s, because S is a communicating class. Yeah? I do not leave the communicating class. So basically I can leave out this condition here, because when I start in I, I'm always going to be in S. And then I just look at the second part, which is sort of not complete now. I should write now not reached I before time n. And this can be related now to the first return time. This indicator here says that I did not reach back to I, so I started in I did not reach back to I before time n. So this means that the first return time of returning to I is greater or equal n. Yeah, so this is the expectation of the indicator function of the set t1i greater or equal n. And of course, the expectation of an indicator function is the probability of the set in question. So this thing now is the sum, n from 1 to infinity, I did not change that, of the probability of starting in I and the first return time to I is greater or equal n. And this sum here is nothing else but the expectation of the first return time. Yeah, we know this from the introductory course. The expectation of a non-negative random variable is in principle the integral of the 1 minus the distribution function. And if it's discrete, if the random variable is discrete, then it's not an integral, but the sum. Finally, we just have to put all the pieces together. So pi is by assumption an invariant distribution. This means that the sum of the pi k equals 1. And we've seen that pi is also the same as pi I times pi bar I. Yeah, so that's what I use now. So pi k is pi I times pi bar k to the I. Yeah, this is this equality here. And the sum here is what we just computed. So this is the expectation of t1. Okay? This whole argument contains a little cheat, or a little simplification, and as with every cheat, sooner or later one is going to find out about it. So this is the moment when we find out that there's something slightly incorrect or slightly missing here. The obvious question somehow is, am I allowed to divide by this expectation here? Yeah, this might be plus infinity, and then, well, I'm not allowed to divide and derive the assertion of the theorem. And the subtle explanation behind this, that this equality here, which actually is this equality, only works when pi I is positive. Yeah, because, well, the invariant distribution is given by a constant multiple of this invariant measure here. If this constant here is 0, then of course the invariant distribution is not 0. Yeah, then just this equality doesn't hold when pi I is 0. So let's settle the easy case first. So if pi I is positive, then this equality works. And then the total equality that you see here implies that the expectation of t is finite. And then you can divide, and then you derive the assertion of the theorem. Yeah? So in this case, everything is fine. Now, how about the case that this expectation here is plus infinity? Yeah, then pi I cannot be positive. Yeah, if it were positive, the right-hand side here is plus infinity, and via these equalities you get plus infinity equal 1, which is not true. So this must imply that pi I equals 0. Notice that in this case the theorem is also correct, because it says that 0 equals 1 over plus infinity. Yeah, so also in this case we can basically rewrite this with the understanding that I just mentioned. Notice that seemingly there's a problem with the proof in this case, because you have 0 here plus infinity, so 0 times plus infinity is supposed to equal 1. But this equality here only holds when pi I is positive. Yeah, otherwise we cannot use this equality here, so there's no problem with the proof in this case also. And I hope I clarified all my cheats now, so this should be the end of the proof of the theorem. I would like to finish this section by noting down one of the results that we proved here, namely this equality, just for future use. Yeah, so in the proof we showed that the sum of the pi bar k is equal to the expectation of the first return time to I. So this is what we had as an intermediate result here, and it's always better to reference a remark rather than later on referencing the proof of a theorem. Also notice that this equality here is independent of our discussion with the pi I positive or something. So this doesn't concern the invariant distribution at all, it just concerns the pi bar. Let me summarize section 3.8. First of all, recall from section 3.7 that there we showed an existence and a uniqueness theorem. Existence in the following sense: so if you are on a recurrent communicating class, then there is an invariant measure. And uniqueness in the following sense: if you are on a recurrent communicating class, then all the invariant measures are essentially the same, meaning they are constant multiples of each other. This section mainly dealt with invariant distributions, and we showed that if there is an invariant distribution, then those states that carry mass of the invariant distribution are recurrent. That was the first main theorem, and a simple corollary was that there are no invariant distributions on transient classes. And then we saw in an example that in transient classes there can be invariant measures, and they can be quite distinct, so they are not necessarily constant multiples of each other, contrary to the uniqueness theorem on recurrent communicating classes. And finally, we saw a relation between the invariant distribution, if it exists, to expected return times.